Okay. So we're talking about the solution of the Dirichlet problem for a complete simply connected Riemannian manifold with pinched negative curvature. So M is complete simply connected Riemannian manifold uh, with pinched negative curvature. And so we're given phi Lipschitz function on the boundary. So here Lipschitz is with respect to an angle metric based at some point P in the manifold M, right? Okay. Here P is an element of M. And this theta P of two boundary points xi eta, this is equal to the Riemannian angle between the unique geodesic rays from P to xi and P to eta. Okay. So this takes values in the interval from 0 to pi. And this is a metric on boundary M. Okay. So first what we did is we defined an extension phi bar from M minus P M bar minus P to R. This is also continuous. So here what you do is you send any point X. So if it lies in M minus P, then it lies on a geodesic from P to some boundary point xi. So you map this to phi bar of X, which you define to be phi of xi. So that means that this extension phi bar, this is constant on geodesics passing through, on geodesic rays starting from P, right? So if we take, let's say, a ray ending at a boundary point xi here, then on this geodesic ray, phi bar is constant equal to phi of xi. Okay. So this is the extension to M minus P. Note that it has a discontinuity at P in general, right? Because as you converge to P from different rays, the limits are going to be, I mean, the values of psi of phi along these rays, which could all be different. If phi is a non-constant function, then this will have a discontinuity at P, right? The limits along different rays ending at P will be different. Okay. All right. But it's continuous outside. And we showed this important estimate that if we're outside a ball of radius rho, and well, if I'm at a distance, say rho from P, let me try and explain it this way. If I take a small ball which is outside this large ball, okay, then what happens is in negative curvature, one can show that the angle subtended by this small ball at the origin. Okay, so I look at the rays passing through this ball. So that gives me some set on the boundary. Okay, that's the shadow of this ball on the boundary. This diameter of this shadow, so diameter with respect to this metric theta p, so diameter with respect to theta p of a ball B contained in M minus ball around P of radius rho, right? This diameter, one can show this is less than a constant times e to the minus a rho. Okay. So this is something which is particular to negative curvature. Okay, so if you stay outside a large ball, then the diameter of a ball which stays outside a large ball, this diameter has to go to zero exponentially. Okay. At a rate which depends on the upper curvature bound A. Okay. So if A is very large, that is, you have large negative curvature, then the diameters of faraway balls decay faster. Okay. So this is not true in this is not true in non-positive curvature. Okay, so in negative curvature, this ball outside the large ball, I can take this very large. So I can take larger and larger balls. In the limit, I could take a horosphere like this outside this ball. Even the diameter of that horosphere will be less than a constant times e to the minus a rho. Okay. So this angle here will be less than a constant times e to the minus a rho. And this one can prove using the hyperbolic law of cosine and using the fact that Riemannian angles are smaller than comparison angles, right? Is this okay? So we did this last time. What we use this to prove is, if I take this function phi bar, so then if I take this ball which is outside the ball of radius rho, if I take, let's say this ball has radius 1 or radius 2, so then if I take any 2 points in this ball, right, then what is phi bar of, so if this is x and this is y, right, then phi bar of x is the same as phi bar of this boundary point, phi of this boundary point, and phi bar of y is the same as phi of this boundary point, and the angle between these two boundary points is less than a constant times e to the minus a rho. So since phi is Lipschitz, that means that mod phi bar of x minus phi bar of y, right? This will be less than or equal to a constant times e to the minus a rho x, where rho x is the distance from P. And this is true for rho x, say greater than or equal to 3, and distance xy less than or equal to 2. Right? This is what we proved. Yeah.
Yes,
is this
sir.
okay?
Yes.
Okay. So notice this property of negative curvature. Let me just explain what happens in non-positive curvature. Right? Non-positive curvature, if I'm outside a ball, let's say in R2, say I'm outside a ball of radius rho, a large ball of radius rho, then if I take balls which are outside this ball of radius rho, right, say they're tangent to this ball at this point, if I make these balls larger and larger, right, in the limit, they converge to a horosphere in R2. What is a horosphere in R2? It's just a plane. It will be the plane which is tangent to this circle at this point, right? So what is the visual diameter of this plane? Well, if I take geodesics along this plane over here and here, right, then as these points go off to infinity, the angle converges to pi, right? So that means this visual diameter is pi, right? Is that clear?
Yes.
So this is something which does not happen in negative curvature. In negative curvature, if you stay outside a ball, then the visual diameter of this ball stays small. Okay, it's less than a constant times e to the minus a rho. So is the difference between the two pictures clear? This is in R2. Okay, here, this theta p diameter of this half plane, of any half plane, no matter how far it is equal to pi. So half plane, this is equal to a horo ball in R2. Whereas here, if I take, horospheres which are outside a large ball like this, if I take a horosphere like this, the visual diameter is going to be bounded above. You see? In negative curvature, the angle stays small. If this horosphere is even further away like this, then the angle is going to become smaller. Do you see the picture?
Yes.
Right?
Yes.
So this is a crucial difference between non-positive curvature and negative curvature, right? This is another difference. Yeah. So horospheres get small in negative curvature as you move away from the origin, whereas in zero curvature, the horospheres will all have the same visual diameter, no matter how far away they are from the origin. Okay. All right. So this is something we're going to need this estimate on the function phi bar. Now what we want to do is smoothen out phi bar into a smooth function. So if we were in Euclidean space, we would just do a convolution, right? So here also what Anderson and Shun do in their manifold is in fact a sort of convolution. So how can we do convolution? Well, if I have a general manifold, convolution means what? It means integral of one function with respect to the translate of another function, right? But the problem is in a general manifold, we don't know how to translate functions, right? So what we can do, however, is we can always translate radial functions. Okay, so convolution with a radial function makes sense actually in any complete simply connected manifold of non-positive curvature. So convolution with a radial function. What does this mean? So suppose say chi is a function which is radial around, or let me call it say u. Say u is a function which is radial around P and M. Okay. So what does that mean? That means that u is equal to some function chi on the real line composed with the distance function from P. Okay. Then we can define for any q in M, define the q translate of u to be, so let me call it tau sub q of u. This is going to be the same function but radial around q now. So this will be chi composed with the distance function from q. Okay. So this is now radial around q. Okay, does this make sense? Yeah. Okay. So now you can define for f and for f in L1 of M devol and so I just need to be able to pair with u. U, let's say, let me just take it in L infinity. Okay, fine. So, I mean, it should make sense for L1 functions also, but I'm not sure. We have to be a bit careful. So let me just take u in L infinity, M, radial around a radial function. Okay. So around P, say. So you define the convolution f convolved with u at Q to be the integral over n f of x into the Q translate of U of x d vol x. Is this clear? Yeah, so this convolution with the radial function, this will make sense in any manifold where the exponential at each point Q is a diffeomorphism from the tangent space to the whole manifold. Okay. So that's all you need. You just need the exponential at each point to be a diffeomorphism. So that is true by the Cartan and Hadamard theorem for complete simply connected manifolds of non-positive curvature. Okay. So there you can define this convolution. And so this is what Anderson and Shen do. They define a convolution. So what they do is you fix a function chi in CC infinity of, say, the interval -2 to 2. Okay, a bump function basically. So such that, say, 0 is less than or equal to chi is less than or equal to 1 on R, and chi is equal to 1 on the interval -1 to 1. Yeah. Ah, right. Okay. So they're not doing exactly a convolution because, okay, yeah. Right. Okay. So, I mean, we can define this convolution in the way that I defined. The only problem is actually, in general, the translates of a radial function, they may not all have the same LP norms. So, or L1 norms. So norm L tau QU L1 norm is not equal to U L1 norm in general. This will be true in a harmonic manifold. Okay. Because in a harmonic manifold, if I take polar coordinates around any point, right, then the volume measure I can write in terms of the Jacobian, right? And the Jacobian is, it only depends on the radius. It's independent of the origin, right? So in a harmonic manifold, the translates will all have the same L1 norm, but this is not true in a general manifold. Yeah. So is that clear? Yeah. Any questions? Yeah. So, you know, you want to convolve with a function whose L1 norm is constant, right? Whose L1 norm is 1, let's say. So it's it defines a probability measure, right? So if the L1 norm is 1, let's say a non-negative function whose L1 norm is 1. So you could take its translates. The problem is the L1 norm of the translates is going to change. Okay. Now it can't change too much if the curvature is bounded above and below by negative constants. It cannot change too much. It will change by some bounded multiplicative factor. Okay. So that's all that can happen really if your function is compactly supported. So here what we need to do is you see you take the function say u sub q of x is chi composed with the distance function from rho from q of x. Now you want the L1 norm to be constant, so you divide by the L1 norm of this. Okay. All right. So this is actually what we have to do, just because of the fact that the L1 norms of the translates are not constant. So actually we do this. Okay. And then we do a sort of convolution. So it's not exactly a convolution. So S phi is defined to be this function. So S phi of x is defined to be integral over n phi bar of x into S phi of let me make this a cube. Okay, S phi of cube. Okay, it's defined to be integral over m phi bar of x uq of x dvol x. Okay. So these uq's are not exactly translates, you see, because I'm dividing by this non-constant factor, right? If this was a harmonic manifold, then this would be a genuine convolution. But since the L1 norms of these translates could change, it's not exactly a convolution. Is this okay? Yeah. So that's the only modification we need to make, because the L1 norm is not necessarily constant. Okay. So what is this function when we write it out? What is this going to be? So this is going to be integral over n phi bar x. So this, what is uq of x? This is chi of the distance from q to x dvol x. And then I have to divide by this L1 norm. So that means divided by the integral over n of chi of distance qx dvol x. Okay. So first of all, notice, why do I want this uq, this to have L1 norm 1? So this uq is greater than or equal to 0, and integral over m of uq dvol is 1, right? So that means then this S phi, this is an average of phi bar, right? This is a weighted average of phi bar, because this uq of x dvol x, this is a probability measure, right? This is a probability measure. So this is some average of phi bar. Okay, and this is an average. This uq is supported, the support of uq is in the ball of radius 2 around Q, right? Okay, because chi is supported in the interval -2 to 2. So chi composed with the distance function from Q, this will be supported in the ball of radius 2 around Q. Okay, fine. Yeah. So let me see. This is what I have here. So let's see. Okay, so actually, so we do something a little different. Instead of looking at the distance chi composed with the distance function, if we want a function which is smooth everywhere, we actually need to look at the square of the distance function, right? Because the distance function itself, it has a singularity at the point from which you're computing the distance, right? It's not smooth at that point, but we know that the square of the distance function is smooth everywhere. Okay, so actually we look at chi composed with this distance function squared. So let me modify this. So what I'm going to do is I look at this distance function squared and I divide by L1 norm of the distance function squared. Okay, so this will actually be this distance squared and this distance squared. Okay. All right. Now it's easy to see that this function, this is a C infinity function of Q by differentiating under the integral sign, right? Is that clear?
Yes. Yes.
Because the Q dependence is only in this term, chi of distance Qx squared, right? Phi bar x, this doesn't depend on Q. So the Q dependence is only in these two terms. So these are smooth in Q. So you differentiate under the integral, you'll get that this is smooth. Okay.
Yes.
So this is smooth by differentiating under the integral sign. Okay. So even though it's not exactly a convolution, it has the same effect as a convolution in that it smoothens the function phi bar, right? It smoothens the function phi bar. Okay. So we get a smooth function S phi. And not only that, because see the support of this U sub Q, this is still contained inside the ball of radius 2, right? Actually, it will be inside the ball of radius square root 2. Okay. Because, I mean, if the distance is bigger than square root 2, then the distance squared is bigger than 2. That means chi of the distance squared is 0, right? Okay, because chi is supported in the interval from -2 to 2. Okay.
Yes.
All right. So what does that mean? That means that if I look at a point on the boundary xi, and if my point Q converges to xi, so there's less than a minute. Let me stop this session and start a new one. Okay. Okay. So if I converge to a point in the boundary, then what happens to this finite ball of radius square root 2, where my function u sub q is supported? Well, this ball also converges to the point xi, right? Because like I said, the visual diameter of this ball, right, this is going to 0, right? This angle here is going to 0 exponentially, as exponentially in the distance of q from P, right? So this angle goes to 0 means that if I take geodesics joining P to these points in the ball, then those geodesics are going to be close to the geodesic joining P to xi, right? So therefore, these geodesics are going to converge to the geodesic from P to xi, right? Okay, so that means in the cone topology, all points in this ball will converge to xi. Okay, in fact, this whole ball will be contained in a neighborhood in the cone topology. In any given neighborhood, for q close enough to xi, the whole ball will also be contained in a slightly larger neighborhood in this cone topology. Is this clear? Right. But now my function phi bar is continuous on m bar minus p. So the values of phi bar in this neighborhood are close to the value of phi at xi, right? And my function s phi of q, this is a average of values of phi bar, right? So if you want, I can write it this way. If I look at s phi of q minus phi of xi, right? Then this I can write as I can take this phi of xi into the integral, because uq has integral 1. So this I can write as phi bar q minus phi xi into uq, phi bar x minus phi xi into uq of x d vol x. Okay. So this phi bar x minus phi xi, this is going to 0, right? Because my integral is actually over a ball of radius square root 2 around q, right? So this integral I can write as an integral over a ball around of radius square root 2. And on this ball, phi bar x is uniformly close to phi xi, the boundary value, right? So that means this goes to 0, okay, as q tends to xi. Is this clear? Yes?
Yes.
Okay. So what does that mean? That means that this function s bar phi, s phi, so thus s phi from m to r extends to a continuous function s phi from m union boundary m to r, such that the boundary value of s phi is equal to phi. Okay. Is this clear? Yes?
Okay.
Is this all right? Yeah. Any
Yes.
question? Rudra?
No, it's all right. Yeah, understand.
So what we've done is we started with the Lipschitz function on the boundary. Now we've got a smooth extension, right? This S phi is smooth in M. So now we've got a smooth extension to the whole manifold. Okay. And not only that, really what we want to show is that actually the first and second derivatives of this S phi, these converge exponentially to 0. Okay, so that means the norm of the gradient of S phi and of the Hessian of S phi, these actually go exponentially to 0. Okay, so for this, let's come to the notes now and see how to prove this. Okay. All right, so let's first look at this function, chi composed with the distance function from y whole squared. Okay. So first of all, what is the L1 norm of this function? So the L1 norm is the integral over m, chi of distance of xy whole squared dvol y. Okay. Now, chi is equal to 1 on the interval from -1 to 1. So that means chi of dxy squared is 1 if dxy is less than or equal to 1, right? So that means on the ball of radius 1, this chi composed with dxy squared is constant equal to 1. So therefore, this integral, this is greater than or equal to the integral over the ball of radius 1 around x, dvol y. So that is the volume of the ball of radius 1. And by the volume comparison theorem, since the curvature is bounded above by minus a squared, the volume of this ball of radius 1, this is greater than or equal to, so remember the volume of balls you get by integrating the volume of spheres from 0 to 1. And the volume of spheres is bounded below by this constant, some Cn minus 1, that's the volume of the unit sphere in Rn, into sin h ar by a into power n minus 1 dr. Okay. So this is some constant which only depends on a, right? This integral is some positive constant which only depends on a. Okay. So we get that these L1 norms of these functions, these are all uniformly bounded below. Okay. Is this all right? Yeah.
Yes.
Okay. Okay. Now let's look at the first and second derivative of these functions. Okay. So let chi bar of t be chi of t squared. Okay. So then chi composed with the distance function from y, rho y squared. This is the same as chi bar composed with rho y. So if I differentiate along a geodesic gamma, starting from x and whose velocity at time 0 is v, which is a unit tangent vector, then what do I have? I have that the inner product between the gradient of chi bar composed with rho y at x, inner product with v. This inner product is nothing but the derivative of chi bar composed with rho y along the geodesic gamma, right? Yeah, by the chain rule, this inner product is just the derivative along gamma of chi bar composed with rho y. So by the chain rule, that is going to be chi bar prime composed with rho y into the derivative of rho y along this geodesic. So the derivative of rho y along this geodesic is the inner product of gradient of rho y with this vector v. Okay. And so we know that the gradient of the distance function, this has norm 1. And so inner product with v is a unit tangent vector. So this inner product has modulus less than or equal to 1 by Cauchy-Schwarz. And this chi bar prime composed with rho y, this is bounded by the C1 norm of chi bar, right? Which is some fixed constant. Okay. So what does that mean? that means that the gradient of this chi bar composed with rho y, this is bounded by the C1 norm of chi bar. Okay. Since this is true for all vectors v, right? That will give you an estimate on the gradient, on the length norm of this vector, right? Okay. So similarly, for the second derivative, if we look at the second derivative of chi bar composed with rho y, so the Hessian applied to v comma v. So for the second derivative, we have to differentiate twice along this geodesic, right? So if I differentiate this chi bar composed with rho y twice along the geodesic, what will I get? I'll get chi bar double prime composed with rho y into the derivative of rho y whole squared, okay, plus chi bar prime composed with rho y into the second derivative of rho y applied to vv. Okay. Now, this sum is going to be less than or equal to some constant k1. Why? Because, well, this chi bar double prime, this is bounded by the C2 norm of chi bar. So that's some constant. And this inner product grad rho y with v whole squared, this is less than or equal to 1. Okay. So this first term is less than a constant, which is the C2 norm of chi bar. And for this second term, this chi bar prime is bounded by the C1 norm of chi bar. And this Hessian of the distance function, this is bounded by a constant because we know that the Hessian comparison theorem tells us the following. So we have to be a bit careful. The Hessian comparison theorem will tell us that this Hessian of the distance function, this is bounded if the distance between y and x is greater than 1, let's say, is bounded away from 0. Okay. If it's greater than 1, then this Hessian will be bounded above. So the point is that if the distance between x and y is less than or equal to 1, then this first term will become 0. Then this chi bar prime will become 0. Because if the distance between xy is less than or equal to 1, then chi bar is constant, right? On the interval from -1 to 1, chi bar is constant. So chi bar prime will be 0 there. Okay. So if the distance between xy is less than or equal to 1, then this second term vanishes because this chi bar prime composed with rho y becomes 0. Whereas if the distance is bigger than 1, distance between xy is bigger than 1, then we use the fact that the Hessian is bounded above. Okay. So let me remind you of the Hessian comparison theorem. So it says that if the curvature is in between minus b squared and minus a squared, right, then the Hessian of a distance function at a point x applied to v comma v, this is greater than or equal to a cot h, a rho y of x into the normal component of v squared and less than or equal to b cot h br b rho y of x into normal component of v squared. Okay. Right. So here, the point is that this upper bound, see, cottage has a simple pole at the origin, right? So as this distance between rho y, I mean, the distance between x and y, if it tends to 0, then this cottage term is going to blow up, right? So that's not good. But the point is, if this distance xy is bounded below, let's say it's greater than or equal to 1, then this will be less than some constant only depending on b, right? If dxy is greater than 1, let's say, and norm v is equal to 1. Is this clear? So here is where we are using the lower curvature bound. Okay, we have an upper curvature bound minus a squared, but we also need a lower curvature bound precisely in this step to get a bound on the Hessian of the distance function. Okay, we need a lower curvature bound here. Okay. Is this okay? Yeah. So finally, what we get is that the norm of the gradient of this chi composed with rho y squared and the Hessian of chi composed with rho y squared, both of these are bounded by some constants independent of y. You see, y was any point in the space. So this is actually not just one function. It is a family of functions, right? So we're getting that for this whole family of functions indexed by points y in the space, all of their gradients and Hessians are uniformly bounded on the whole space. Okay. Is this clear? Yeah. So now we can estimate. So, okay. So we define this function S phi. This is the definition that we gave earlier, right? Okay. And so this function S phi is C infinity on M, and it converges to phi of xi as x tends to xi in boundary M. So it's a continuous function on M bar whose boundary value is equal to phi. Now comes the main lemma which we need, that there is a constant C double prime positive such that the norm of the gradient of S phi of x and the norm of the Hessian of S phi of x, okay, both of these are less than or equal to this constant C double prime into e to the minus a rho x, where rho x is the distance from the origin. Okay. So the point is that these gradient and Hessian, they decay with the same exponential growth rate a, okay, which only depends on the upper curvature bound. So let's first prove the estimate on the gradient, and then we'll see that similarly one can prove the estimate on the Hessian. So let's look at the gradient of S phi of x, the gradient of S phi at a point x. So now what we can do is we can, since we're looking at the gradient, we can subtract a constant from the function, right, without changing its gradient. So this gradient is the same as the gradient of S phi minus phi bar of x. Okay, phi bar of x is just a constant here, okay? But the point is, when I do this, then this S phi is in terms of an integral. I can bring this phi bar of x into the integral, right? Because it's an integral with respect to a function of mass 1, right? Okay. Yeah. I'm integrating with respect to a function whose total integral is 1, right? So I can bring this constant phi bar x, I can bring it into the integral. Okay. So now what do I get? I have the gradient in the x variable of this function, chi of distance xy squared into phi bar y minus phi bar x integral dy divided by integral chi of distance xy squared dy. Okay. Is this all right? Yeah. So, so by differentiation under the integral sign and the quotient rule, what will the gradient of this ratio be? Right? I mean, both numerator and denominator are functions of x, right? Here, y is a dummy variable. You're integrating with respect to y. Both of these are functions of x. So we're taking the gradient in the x variable. Okay. So by the quotient rule, the gradient is going to, or the product rule, if you like, let's say the product rule, gradient is going to be gradient of the numerator divided by the denominator. And then minus numerator into gradient of the denominator divided by the denominator squared, right? This is the quotient rule. Yes? Okay. So
Yes.
what is the gradient of the numerator? So by differentiation under the integral sign, it is going to be the gradient of each of these terms, right? Gradient of chi composed with rho y squared, okay, at x into this constant phi bar y minus phi bar x dy, okay. And here I'll get what? Minus chi of dxy squared into phi bar y minus phi bar x dy divided by this whole squared, integral of chi dxy squared dy whole squared into the gradient of chi composed with rho y squared, which is chi bar composed with rho y, okay, dy. So now we have a bound, a uniform bound on this gradient of chi composed with rho y squared. This we just proved. This is less than a constant, independent of y and x. And we have a lower bound on this denominator, right? This integral of chi of dxy squared dy, this we know is bigger than some constant depending on a, right? So I have a lower bound on the denominator. So therefore, I'll get an upper bound on 1 over this, right? And I have an upper bound on this numerator. Yeah. So what will I get? Finally, I'll get that this norm of the gradient of s phi at x, this is less than a constant times. So notice these integrals, these are over the ball of radius 2 around x, right? Because this chi composed rho y is supported inside the ball of radius square root 2 actually. So these integrals are over at most the ball of radius 2. And so then I'll get that this norm of the gradient is less than a constant times the sup over y in the ball of radius 2 around x, phi bar y minus phi bar x. Okay. Is this clear?
Yes.
Okay, because I mean, see, this norm of this gradient term, this is going to be bounded. This chi of dxy squared, this is bounded. This gradient of norm, a gradient of chi bar composed rho y, this is some bounded thing, right? And I'm integrating over a bounded ball. So a ball of bounded radius, yeah. And this denominator is bounded below. So in all these bounds, I'll just get constant times the sup norm of this phi bar y minus phi bar x, right? This factor I'm going to get, the sup of phi bar y minus phi bar x. The rest will give me some constant. Okay. Is this clear?
Yes.
Okay. And similarly, if we look at the Hessian of S phi, then again I write it as the Hessian of S phi minus the constant phi bar x. And this I write as an integral as earlier. And then you compute the Hessian. So that's a longer computation. But at some point you'll see a term like this, the Hessian of chi composed with rho I squared, which we saw this Hessian is bounded uniformly. Okay. Then one can show that similarly we have an estimate, Hessian of S phi at x is less than or equal to constant times sup over y in the ball of radius 2 around x, phi bar y minus phi bar x. Okay. Is this all right? Yeah.
Yes. Yes.
But now we know from the previous lemma that this supremum, phi bar y minus phi bar x, this goes to 0 exponentially, right? In the distance of x from the origin. So this is less than a constant times e to the minus a rho x. Okay. So this is when x is outside the ball of radius 3. We have this estimate. And inside the ball of radius 3, by continuity, the norm of the gradient and the norm of the Hessian are bounded on the compact ball of radius 3. Therefore, this same inequality will hold on all of M if I choose this constant large enough. Okay. Is this clear?
Yes, sir. Yes.
Okay. So the norm of the gradient and the Hessian, they go to 0 exponentially. And what's important is that the rate of decay is at least this e to the minus a rho. Okay, the coefficient is a here. Why is that important? That is important because then we can see that if we take a real number, a positive number delta, which is small enough, so let's say it's smaller than n minus 1a and smaller than a. So, okay, this is there's a typo here. This should be a here and this should be n minus 1a on the right hand side. These two should be interchanged. So if I take delta to be a over 2, then if c is a large enough constant, then the functions phi plus, which is s phi plus c times e to the minus delta rho, and phi minus, which is s phi minus c times e to the minus delta rho, these are going to be superharmonic and subharmonic respectively on M. Okay. So let's, we just need to calculate the Laplacian, right, of these. So if delta is less than or equal to A, then notice that e to the minus delta rho is greater than or equal to e to the minus a rho, right? So on M minus singleton P, the Laplacian of phi plus, so this is the trace of the Hessian of S phi plus c times the Laplacian of e to the minus delta rho. And we know that the norm of the Hessian is decaying exponentially, right? So the trace of the Hessian is going to be less than or equal to n times the norm of the Hessian, right? So this is less than or equal to n times c double prime e to the minus a rho, right? And this Laplacian of e to the minus delta rho, this function we saw this was superharmonic. Its Laplacian is negative. This will be minus c times a over 2, that is my delta, into n minus 1 a minus a over 2, right? Into e to the minus delta rho. Okay. And since e to the minus delta rho is bigger than or equal to e to the minus a rho, if I have a minus sign here, then minus e to the minus delta rho is less than or equal to minus e to the minus a rho. So I can replace this e to the minus delta rho by e to the minus a rho. And I put these two terms together. So then I'll get e to the minus a rho into nc double prime minus, what will I get here? So here I'll get n minus 3 halves into a and then into a. So I'll get a squared over 2 into n minus 3 over 2 into this constant c. Okay. Now c double prime is fixed, a is fixed, n is fixed. So if I choose c large enough, then this term in brackets is negative, right? So therefore the whole thing will be less than or equal to 0. Okay. Is this clear? Yes?
Yes, sir.
Okay. So similarly, we can show that the Laplacian of s phi minus c times e to the minus delta rho, that will be greater than or equal to 0. Okay. Same kind of calculation will give you that this is greater than or equal to 0 on m minus p if c is large enough. So therefore, phi plus is superharmonic and phi minus is subharmonic on m minus p, and both are continuous on m. Therefore, it's easy to see, like we gave the argument last time, that phi plus and phi minus will actually be superharmonic and subharmonic on all of m, right? Okay. We did this argument before, right? If you have a function which is, let's say, superharmonic outside a point and continuous at the point, then it is superharmonic everywhere, right?
Yes.
Okay. Okay, so we get functions phi plus and phi minus, which are superharmonic and subharmonic on M. What is the point now? The point is, if you look at these functions, phi plus and phi minus, what are their boundary values? As you tend to the boundary, S phi converges to phi, and this e to the minus delta rho, this goes to 0, right? Rho is the distance from the origin. That goes to 0 as you converge to the boundary. So these terms disappear. So that means phi plus and phi minus, both of these have the same boundary value phi. But one is superharmonic and the other is subharmonic. Right? Well, that will tell us that we can now use the Perron method. We can use these functions as barriers in the Perron method to solve the Dirichlet problem. Okay? So now we can solve the Dirichlet problem using the Perron method, right? So we first solve the Perron, the Dirichlet problem for Lipschitz functions, right? So all of this we've been doing for a Lipschitz function. So let phi be a Lipschitz function on boundary M. So then there exists a unique u phi, which is C2 on M and C0 on M closure, such that Laplacian u phi is 0 on M and u phi is equal to phi on boundary M, right? So what do? We now take the Perron family for the whole space. So that means I look at u in C0 of M closure, okay, such that u is subharmonic on M and u is less than or equal to phi on boundary M, okay? And as before, I put u phi of x, the Perron solution, to be the supremum of u in f phi of u of x. Okay, x in M. Okay, so note, I mean, my function phi on boundary M, this is Lipschitz, so it's continuous, so it's bounded above and below. So this Perron family is non-empty. I can just take any constant c which is less than or equal to the infimum of phi, right? That will belong to the Perron family. It will be continuous on M bar and less than or equal to phi on boundary M. So this Perron family is non-empty, and by the maximum principle, all of the functions in the Perron family are bounded above by the supremum of phi, right? They're bounded on the whole space by the supremum of phi, by the maximum principle. So this supremum of u of x over functions u in the Perron family, this supremum is finite, right? Okay. And then by the same argument that we gave earlier, this Perron solution u phi is harmonic. Okay. So we get a harmonic function from the Perron family as before. All that you have to show is that it has the right boundary values, right? You have to show it takes the right boundary values, that it converges to phi, right? For that, we use these superharmonic and subharmonic functions phi plus and phi minus. Okay. So notice phi minus on the boundary, it is equal to phi, and phi minus is superharmonic. Phi minus is subharmonic. So therefore, phi minus belongs to the Perron family, right? Yes? Phi minus belongs to the Perron family. Therefore, by definition, the Perron solution u phi is greater than or equal to phi minus on M, right? So therefore, if we take a boundary point xi in boundary M, then the lim-inf as x goes to xi of u phi x, this is greater than or equal to the lim-inf as x goes to xi of phi minus of x, and that is equal to phi of xi. Right? We know that phi minus has the boundary value phi, right? So this lim-inf is going to equal phi. So therefore, we get one inequality. The lim-inf of u phi is greater, as x tends to xi, is greater than or equal to phi xi. Okay? Fine. Now we want to show the lim sup is less than or equal to phi xi, and then we'll be done, right? So let epsilon be positive, and let u be a function in the Perron family f phi. Okay. Now u restricted to boundary M, this is less than or equal to phi, which is the same as phi plus restricted to boundary M, right? So since u is continuous, u is continuous on M bar. Okay. Notice that functions in the Perron family, by our choice, they're continuous on M bar. Okay. So if the boundary value, if u is less than or equal to phi plus on M bar, on boundary M, so that means if I look at the function u minus phi plus, that is continuous on M bar, and it is less than or equal to 0 on boundary M. Therefore, by continuity, if I choose okay. Fine. So we've proved that the lim-inf of u phi x as x tends to xi is greater than or equal to phi xi. Now we want to prove that the lim sup of u phi x is less than or equal to phi xi. So we let epsilon be positive and take a u in the Perron family. So then u restricted to boundary M is less than or equal to phi, which is the same as phi plus restricted to boundary M. That means that u minus phi plus that is less than or equal to 0 on boundary M. Therefore, by continuity, if you take an R large enough, then U minus phi plus is less than or equal to epsilon on the boundary of this large ball, right? So in other words, U minus epsilon is less than or equal to phi plus on the boundary of the ball B, right? Okay. But now U minus epsilon is subharmonic and phi plus is superharmonic. So if you have this inequality on the boundary of the ball B, then you will have the same inequality on the whole ball B, right? Is that clear? By the maximum principle, if I look at U minus epsilon minus phi plus, that is going to be subharmonic and less than or equal to 0 on boundary B. Therefore, it is less than or equal to 0 on B. Is that clear? Okay.
Yes, sir.
Therefore, what do I get? Therefore, I get U is less than or equal to phi plus plus epsilon on the ball B. Okay. So now this ball B, I can take as large as I want, right? So since I can take this ball to be as large as I want, I get that finally U is less than or equal to phi plus plus epsilon on all of M, right? For all U in F phi. Okay. Is this clear?
Yes, sir. Yes.
Yeah. See, here this ball I was choosing as large as I want, right? I just chose a large enough ball, right? So I can, if I take this ball larger and larger, I'll get the same inequality on larger and larger balls. And so I'll get the same inequality on all of M, right? Okay. So therefore we get that U is less than or equal to phi plus plus epsilon on all of M. And here U was an arbitrary element of the Perron family. Therefore, now we can take supremum over the Perron family. And then we get that U phi is less than or equal to phi plus plus epsilon on all of M. Okay. Therefore, the lim sup of U phi as x goes to xi is less than or equal to the lim sup as x goes to xi of phi plus x plus epsilon. And that is equal to phi of xi plus epsilon. So since epsilon was arbitrary, letting epsilon tend to 0, we get that the lim sup of U phi x is less than or equal to phi xi. And therefore, we get that the limit of U phi x is equal to phi xi for all xi in boundary M. And so there we are done. Okay. Is this clear? Yeah. So the point was to construct subharmonic and superharmonic functions whose boundary values are equal to phi. That was the point, actually. Once you have that, then the rest is just a simple application of the Perron method. The Perron method will work and give you the correct solution of the Dirichlet problem. Okay. The main work was to construct these superharmonic and subharmonic functions, phi plus and phi minus, which have the same boundary value as phi. Okay, that was the main work. In other words, constructing superharmonic and subharmonic extensions of phi, right? Once you've constructed the superharmonic and subharmonic extensions of phi, then by using the Perron method, you will get the harmonic extension of phi. That's the idea. So once you have it for Lipschitz functions, then you get the solution of the Dirichlet problem for general continuous functions. Okay, so if suppose phi is a continuous function on boundary M, then there is a unique U phi in C2M in intersect C0M closure, which is harmonic on M and whose boundary value is equal to phi. So how do you do this? Well, you approximate phi by Lipschitz functions, right? So the point is that, I mean, smooth functions on the sphere TP1m, these are dense in continuous functions on the sphere, and smooth functions are Lipschitz, right? So therefore, given any phi, which is a continuous function on boundary M, we can find a sequence of Lipschitz functions phi n on boundary M, which converge uniformly to phi on boundary M. Okay. So then for the Lipschitz functions phi n, we have a solution u sub phi n. Let me call that un. Okay. So then by the maximum principle, I know that the sup norm of un minus um over M closure is equal to the sup norm of over the boundary, which is the sup norm of phi n minus phi n over boundary M. And this sup norm goes to 0, right? Because the phi n's are converging to phi uniformly on boundary M. Okay. So that means that my un minus um, this sequence is uniformly Cauchy on M bar, right? This sequence is uniformly Cauchy on M bar. Therefore, it converges uniformly to some function u, which is also continuous on M bar, right? And moreover, because the convergence is uniform and the UNs are converging, their boundary values are converging to phi, that means that the boundary value of u has to equal phi, right? Okay. So this is all because we have uniform convergence on M bar, on the compact space M bar, right? So uniform convergence on M bar implies that we get a function u whose which is continuous on M bar and whose boundary value is phi. And then by what we did earlier, you know that if you have harmonic functions which converge uniformly on compacts, then the limit is also harmonic, right? That we've seen before. And so this u that you get is the solution of the Dirichlet problem. That's it, basically. That's it. Okay. So that's it. Yeah. So that finishes the solution of the Dirichlet problem at infinity. Okay. So now any questions? So notice this lower curvature bound was only used in one place really, to bound the Hessian of the distance functions in the Hessian comparison theorem. Okay. That's where the lower curvature bound came in, to bound the Hessian of the distance functions. And I should mention that if you do not have the lower curvature bound, then in fact, the Dirichlet problem need not be solvable. There are counterexamples where you have negatively curved manifolds, complete and simply connected, but which have negative curvature going to infinity, where the Dirichlet problem does not have a solution. Okay, so this can happen. So that means the lower curvature bound is necessary in some sense. Okay. You do not have a solution to the Dirichlet problem for all negatively curved manifolds. You do need some lower curvature bound. Okay. You do need some lower curvature bound. So, any more questions?
Another thing, you have always assumed simply connectedness, right? That is yes.
Right, right.
So for
Yeah, actually, yes, go ahead.
Yeah, for hyperbolic manifolds, you may not get.
Well, actually, what happens is, see, the boundary, if the manifold is not simply connected, I mean, you can still define the boundary, but it won't be a nice space in general. Like, for example, so if the manifold is compact, for example, then the boundary is trivial, right? It's just a point, because, I mean, all geodesics, the whole manifold is bounded, right? So the distance between any two geodesic rays is always bounded, right? So there's only one equivalence class, the boundary is trivial. So here it doesn't really make sense. Even if you take a manifold which is, let's say finite volume, so say with a cusp like this.
So G by
Okay.
K by gamma.
Exactly, right. So a locally symmetric space, right? Say of finite volume. Even here, the boundary will be trivial. Because so let me think a second. So if I have two geodesics below which are at bounded distance from each other, then in the universal cover, which is the disk, I get two geodesics which are the lifts. I get two lifts which are at bounded distance, so they end at the same boundary point. Okay, fine. Yeah, I think the boundary will probably be just 2 points. You see, let me just think a second. 1 second. Sorry. No, there could be geodesics which go into the cusp and come back out and then go in again. Yeah, that could happen. That could happen. I mean, essentially what happens is the boundary of, let's say, H2 mod gamma, this should be identified with boundary of H2 mod gamma, right? Because I have a map from boundary H2 to boundary of H2 mod gamma. Where I just take an equivalence class and I take the equivalence class of pi composed with gamma, where pi is the projection from H2 to H2 mod gamma, right? If gamma is a geodesic in H2, then its projection is a geodesic in H2 mod gamma, right? And so I can take its equivalence class, right? So this map, this map is going to be surjective. And I want to say this is identified with boundary H2 mod gamma, right? So when do 2 points map to the same equivalence class below? Right. So, I mean, if let's say, if pi composed gamma 1, so if pi composed gamma 1 is equal to pi composed gamma 2, this is if and only if pi composed gamma 1 is equivalent to pi composed gamma 2. Okay, so that means, so I have, say, a gamma 1 and I have a gamma 2. And I'm saying that their projections are equivalent below, right? Okay, the projections are equivalent below. So maybe they look like this. Okay, this is, say, pi composed gamma 1. And this is pi composed gamma 2. But if the projections are equivalent below, right, what I can do is I can lift them. This happens if and only if there exists a lift of of pi composed gamma 1, which is equivalent to a lift of pi composed gamma 2.
Right.
They have equivalent lifts, right? But then what are the lifts of pi composed gamma 1? That means the lifts of pi composed gamma 1 are just gamma 1 and all its gamma translates, all its translates under the discrete group gamma, right? These are all the lifts of pi composed gamma 1. So that means there exists gamma in gamma such that gamma, oh no, bad notation. There exists G in gamma. Sorry, there exists G in gamma such that G gamma 1 is equivalent to gamma 2, right? So you get a picture like this. This is G gamma 1. Yeah. So in other words, that means that if and only if G dot gamma 1 is equal to gamma 2 for some G in gamma, right? So once you have this, from this, I think it's easy to see that this map induces a bijection, right? From del H2 mod gamma to del of H2 mod gamma, right?
Yeah.
Is it clear? Yeah. Okay. So we get this identification. Del of H2 mod gamma is del H2 mod gamma. And then what that means is that the point is, for most groups, the gamma action on the boundary, say if you take a finite volume group, then all the orbits are dense. Okay, all the orbits are dense. So this quotient will be non-Hausdorff. It will be some bad space. Right, that means basically it will be a space where one point is dense in the whole space. Right? It's like the quotient of a torus by an irrational slope line, right? That gives you a non-Hausdorff space where each point is dense in the whole space. So it gives you a very pathological space. So in these cases, the boundary is not nice. So one doesn't really look at the Dirichlet problem there. Right? In a sense, the boundary becomes a point, right? Because one point is dense in the whole space. So, I mean, you have a continuous, any continuous function on the boundary has to be constant, right? Because a point is dense in the whole space. So that means if you have a continuous function, then it has to be constant, right?
Yeah.
That's it. So, And you can also see it this way, that continuous functions on the boundary of H2 mod gamma are the same as continuous functions on the boundary of H2, which are gamma invariant, right? But if the gamma orbit is dense and a function is gamma invariant, then it is constant on the orbit, which is dense. Therefore, it's constant everywhere, right? So in this case, the continuous functions on the boundary become trivial. They're just constants. So that's why it's not so interesting. So it's only when you take the full universal cover, where gamma is just the trivial group, then you get a nice boundary, which is a sphere. And then you have the usual continuous functions on the sphere. So I think that's why. I mean, there are intermediate cases. There are these so-called convex co-compact groups. So for those, you do have something on the boundary. So Convex co-compact means that, for example, it looks like, what would it be? So for example, a sphere minus 3 disks, okay, as a Riemann surface. If I take the corresponding hyperbolic metric on this 3-hole sphere, so that these are not points, these are disks, okay. So if I remove disks, there's a metric on this which will make it look like basically a compact surface with boundary, a 3-hole sphere with boundary, what's called a pair of pans. Okay. And then you have these flaring ends, these non-compact ends, which go out like this. So this is called a convex co-compact group, this corresponding fundamental group acting on H2. Okay. And for this, what happens is the action of the group on the boundary. So in this case, not all orbits are dense. The orbit of a point, well, in the inside, it accumulates on what's called the limit set, and the limit set is a Cantor set on the boundary. So you'll be throwing away some intervals, yeah, and then further throwing away and so on, and taking out intervals. And you'll get a Cantor set on the boundary, and the complement of that Cantor set, there the group action is properly discontinuous. Okay, so that's some open set on the boundary. There the group action is properly discontinuous. So when you take the quotient, it doesn't collapse to points. Yeah, you'll get some quotient. Yeah, that makes sense. I mean, yeah. So I mean, if you do this in higher dimensions, what happens is, for example, you take a Fuchsian group. So, right. So if you take, let's say, gamma is a discrete subgroup of PSL2R, and you embed this into PSL2C, okay, which you identify with the isometry, orientation preserving isometry groups of H3, okay. So now you have a Fuchsian group acting on the unit ball in 3 dimensions, okay. So what it's going to do is, it's going to leave this equator. This is a copy of H2, and here you have H3, okay. So gamma is going to leave this copy of H2 invariant, okay. And the limit set of gamma is going to be actually some subset of this equator, okay. The limit set is going to be a subset of the equator. So suppose gamma is, let's say, let's say that the H2 mod gamma is compact, okay. Suppose H2 mod gamma is compact. In that case, the limit set is going to be this circle S1 sitting inside S2, okay, which is the boundary of H3. So limit set means the set of accumulation points of any orbit, any gamma orbit. Okay, so any gamma orbit is going to accumulate on this whole circle. All right.
Okay.
Yeah. And what happens is the complement of this limit set. So if I take the boundary of H3 minus this limit set, this is some open set, right? So let me call this O sub gamma. This is an open set in the boundary. And this open set here this modulo gamma, this quotient is nice. So what happens is the upper hemisphere and the lower hemisphere, these are invariant. Okay, so this thing is nothing but upper hemisphere. So let me call that, say, U plus, disjoint union U minus, right? Upper and lower hemispheres. Okay, so the quotient of the upper hemisphere acting on the upper hemisphere, it's going to be a co-compact group. So you'll have a compact fundamental domain. Okay, and it's going to be a surface of some genus G. So what will happen is basically you'll get two Riemann surfaces. The quotient will be sigma 1 disjoint union sigma 2. Okay. And so in that sense, I mean, the boundary of H3 mod gamma, this you identify with boundary H3 mod gamma. Okay. And this is the limit set mod gamma disjoint union. This open set is called the domain of discontinuity mod gamma. So this part, the limit set mod gamma, this is bad. This is like a point. Okay. But this part is nice. Okay. This is bad. This is like a point. This part is nice.
Right.
This is a union of two Riemann surfaces. These are Riemann surfaces. Or yeah, these are Riemann surfaces. Okay, so in this case, the boundary of this locally symmetric space H3 mod gamma, this becomes a union of two Riemann surfaces. Yeah. So there you can talk about continuous functions on the boundary and so on. Yes. But I mean, the point is, see, if you can solve the Dirichlet problem for the universal cover, then you can solve it for any quotient, right? Because you take a continuous function on the boundary of the quotient that you can lift to a gamma invariant continuous function on the boundary of the universal cover, right? And then once you have a continuous function on the boundary of the universal cover, there you know that the Dirichlet problem is solvable. We've just given the solution. So you solve it on the universal cover. And then because the boundary function is gamma invariant, the harmonic extension will also be gamma invariant. Therefore, it will again descend to a harmonic function on the quotient.
Okay.
Does that make sense? Yeah. Right,
Okay,
because I mean, the gamma action commutes with the Laplacian, right? So
yeah, that's true. Yeah.
So if the boundary function is gamma invariant, then the harmonic extension will also be gamma invariant, right? Because I mean,
so you got a harmonic function on the quotient.
So you get a harmonic function on the quotient, exactly. So it suffices to solve the Dirichlet problem for the universal cover, which is always simply connected. That's why we only look at the simply connected case. I mean, the other cases follow from the simply connected case. Yeah, that's it. But just by gamma invariance of the solutions, so you can always push them down to the quotient and you get your solution below. That's the idea. Yeah, so that's why we look at the simply connected case. So more questions?
We defined a general notion of convolution Do we have some analogy with like Young's inequality?
Sorry, with what? Young's in maybe, I don't know. I haven't thought of for harmonic manifolds. Yes, I think probably yes. Yeah.
For harmonic manifold, you
For
have done
harmonic,
something. I mean, like Kunjasman
yes, yes,
phenomenon.
correct. Yes, yes. For harmonic manifolds, many of the usual things about convolution go through, right?
Okay.
But for general manifolds, you can see that, you know, the translation doesn't preserve L1 norm, right?
Yeah.
So
Yeah, that's why I'm asking.
yeah, that's going to give a little problem. So yeah, so for general manifolds, it's not so. Even here, we didn't do exactly a convolution, right? We did sort of a convolution, but we
No, that's
normalized
first
so
one.
that the L, yeah, we divide by the L1 norm of the translate, right? So it's not exactly a convolution. It's some nonlinear
Yeah,
operation.
translation is not norm
Yes.
preserving. So
It's not norm preserving. Exactly. The point is translation is not norm preserving. So you have to divide by the norm in order to stay norm, you know, to preserve the norm. And once you do that, then the operation becomes non-linear, right? It's not a linear operation anymore.
Yes, yes.
Okay, so maybe the last thing I wanted to say, just to finish the course, is that you can define, just like we did for a finite ball, using the solution of the Dirichlet problem, we defined harmonic measures on the boundary of the ball. The same, exactly the same procedure gives us harmonic measures on the boundary at infinity, right? You basically, to define the measures, you need to define a positive bounded linear functional on the space of continuous functions on the boundary, right? So every point x gives you such a functional. Phi goes to u phi x, right? And then by the maximum principle, this is bounded of norm at least one. Again, by the maximum principle, this is a positive functional. And therefore, applied to the constant function 1, it just gives 1. So therefore, this gives you a probability measure, right? Is this clear? It's the same procedure as we did for a finite ball. So you have for this whole space. So you get a probability measure called the harmonic measure based at x, which is a probability measure on the boundary now. Okay. And so, yeah, I did do some more things. These probability measures, these are mutually absolutely continuous. Okay. So in fact, mu x is less than a constant, e to a constant times the distance between x and y times mu y. Okay. So to see this, what you do is, it's enough to show that the integral of any non-negative function phi d mu x is less than or equal to e to this constant dxy times the integral of phi d mu y, right? So what are the integral of phi d mu x? It's the solution of the Dirichlet problem, right? With value at x, its value at x, and the integral d mu y is the solution of the Dirichlet problem, its value at y. So we just need to estimate non-negative harmonic functions at x and y, and that we know how to do, right? By the Harnack-Yau inequality, right? By the Harnack-Yau inequality, we get that if phi is a positive function, then the harmonic extension u phi is positive by the maximum principle. And for a positive function, we have the Harnack-Yau inequality on a finite ball. Letting the radius of the ball go to infinity gives you that the norm of the gradient of log u phi is uniformly bounded by a constant. And then you just integrate this, right? To get that u phi of y is less than or equal to e to the constant times the distance from x to y into u phi of x. And that gives you the inequality between the harmonic measures, right? The u phi of y is the integral of phi d mu y. This is less than e to the c naught r naught integral of phi d mu x. So this is true for all phi positive. And from that, it's easy to see the measures satisfy the same inequality, right? Is that clear?
Yes.
Okay, so what this means is actually there is a measure class on the boundary, which is called the harmonic measure class, right? All of these have the same measure zero sets, right? All of these have the same measure zero sets. So you get this harmonic measure class on the boundary. And because these are mutually absolutely continuous, we can define their Radon-Nikodym derivatives. So that gives us what's called the Poisson kernel of the whole space, right? So the Poisson kernel is defined to be a function of two variables, x and xi. It is the Radon-Nikodym derivative of d mu x with respect to d mu 0, where 0 is a fixed base point, right? So once you have this, then you get the general Poisson formula for any continuous function on the boundary. The solution to the Dirichlet problem is given by the Poisson integral. U phi of x is integral over boundary M. Phi xi, px xi, d mu naught of xi. Okay. Is this clear? Yeah. And so we have a Poisson transform also. The Poisson transform goes from L1 of the boundary into harmonic functions in the inside. You just define it to be this Poisson integral. Okay. So what you have to show is that this Poisson integral is harmonic. So that's done in these notes. It's not too hard to do. And then there's some business I did at the end where basically what I wanted to show is, let me just, is something about the domain of the Poisson kernel. So yeah, this is something which Anderson and Shun, they prove something much stronger, but without doing as much as they do, I mean, the point is that okay, so will you give me just 5 minutes to wrap things up? There's about a minute
Sure,
left.
sir, sure.
If you give me 5 minutes, I'll just wrap things up, and that'll more or less finish the course. So just give me another 10 minutes. I'll wrap things up then. Okay. So, okay. So let's just start one last session and then we'll stop. Okay, so about the domain of definition of the Poisson kernel, actually one needs to be a little careful here. The way we've defined it, you see, we defined for each x, we define the Poisson kernel as a function of xi on the boundary.
You should
It is
share
this
your screen.
Oh, sorry. I forgot to share the screen. Sorry. Yeah, okay. So about the domain of the Poisson kernel, right? So for each x, we're defining the Poisson kernel as a measurable function on the boundary, right?
Right.
Which is the Radon-Nikodym derivative, d mu x, d mu naught of xi. Now, the problem with this is that the Radon-Nikodym derivative is only defined up to sets of measure 0, right? It's not uniquely defined as such. It's only up to sets of measure 0, right? So that means for each x, we're getting some full measure set on the boundary where this, some full measure set of xi, right? But that full measure set could depend on x, right? And here we have x is ranging over the whole space. So there are uncountably many x's. So, you know, if x was ranging over a countable set, then for each x, you have some full measure set in xi. You take the intersection of those full measure sets. A countable intersection of full measure sets is also full measure, right? So then you'll get a full measure set which works for all x. That would be true if x was a countable, you know, if the space was countable, but the space is uncountable, right? So you can't a priori just take an intersection and, you know, you won't get a full measure set in general, right? So So instead, one needs to do just a little bit of work to say that actually there is a single full measure set E which does not depend on x, such that the following holds. We can define a function p from m cross E to 0 infinity. So E here is a subset of boundary M, a full measure subset, such that for all x in M, d mu x, d mu naught of xi is equal to p of x xi for mu naught almost every xi in E.
Right. Okay.
Okay, so this same set E works for all x. That is the point here. Okay. This same full measure set works for all x. And moreover, for every xi in this set E, if I now for every xi in this set E, I have a function of x. It's defined for all x. So this function, x goes to p of xi. This is harmonic on M, right?
Right.
So this is what I want to do. So let's just do this. So the idea is the following. You take a xi to be a countable dense subset of M, okay? Then by Lebesgue differentiation theorem, okay, so since the boundary is identified with Sn minus 1, which is Rn minus 1 union a point. So by Lebesgue differentiation theorem, for each I, there is a full measure set EI in the boundary of M, such that for all xi in EI, the Radon-Nikodym derivative d mu xi d mu naught of xi is equal to a limit m tends to infinity mu xi of the ball of radius 1 over m over at xi divided by mu naught of the ball of radius 1 over m around xi, right? Yeah, this is by a version of Lebesgue differentiation theorem, right? Yeah. So for each I, I'm getting a full measure set EI. Okay. Now, what is this ratio of harmonic measures? Well, this mu xi of this ball, this is nothing but the Poisson transform of the indicator function of this ball, right? At the point xi.
Okay.
Right? Because what is the mu xi? It means the integral of the integrator function, right? So integral of the integrator function at xi.
That is true.
That is just the Poisson transform, right? That's just the Poisson transform. Okay. So I have this. Okay. So now what I can do is so this is true. So this is the limit as m tends to infinity. Okay. So now what I do is I have a countable collection of full measure sets. I take E to be the intersection of the EIs. Okay. Now if I take xi is a point in this intersection E, I define a function f of xi comma m of x, which is this Poisson transform. Indicator function b xi 1 over m divided by mu naught of b xi 1 over m, this at x. Okay. So this Poisson transform, one can show, that's not hard to show. This is a harmonic function of x. Okay. This is a harmonic function of x. And so this is non-negative, harmonic, and its value at the origin at 0 is equal to 1, right? If I put x equal to 0, then this becomes just mu 0 divided by mu 0. So this becomes 1. Okay. So so these are a sequence. If I fix xi and look at m varying, this is a sequence of harmonic, non-negative harmonic functions whose value at the origin is fixed, equal to 1. therefore, by the Harnack-Yau inequality, this sequence is going to be equicontinuous on compacts and also uniformly bounded on compacts, right? Okay. So, moreover, what can I say about any limit of the sequence? Well, any limit of the sequence as m tends to infinity, I know that this converges to, at the point xi, this converges to d mu xi d mu naught of xi, right? By definition. Yeah. Okay. So that means that if I take any limit function of this sequence, then on the dense set xi, any two limit functions are equal, right? And any limit function of this sequence is harmonic, because it's a uniform limit on compacts of harmonic functions. So it's harmonic. So if you have two harmonic functions which are equal on a dense set xi, then they are equal everywhere, right? So that means if you have a sequence which is equicontinuous and uniformly bounded, such that all limit points are equal, there's a unique limit point of the sequence, then the whole sequence is convergent, right? Is that clear?
Yes.
Yeah, this is the standard argument when you work with normal families, right? If you have a normal family such that all limit points of the normal family are equal, then the normal family itself is convergent,
Yes,
right?
yes.
So that's all. That's all. So all limits are equal. So therefore, the whole sequence is convergent. So therefore, the whole sequence, it converges uniformly on compacts to a positive harmonic function, which we can call f sub xi. So this is now defined for all xi in E. Okay. Now we define our function p of xi as f sub xi of x, where x is in M and xi is in E. So this is defined on M cross E. Okay. So then what I want to say is that by construction, the property 2 holds that for all xi in E, p of xi is harmonic on M, right? That holds because these functions f xi that I'm getting, these for a fixed xi, f xi is a harmonic function on x, right? So property 2 holds. Okay. Now, what about property 1? This p of xi, this should equal the Radon-Nikodym derivative d mu x d mu naught for almost all xi, right? Okay. So let's look at what happens. If I take any x in M, then I have a full measure set E sub x in boundary M by Lebesgue differentiation theorem, such that d mu x d mu naught of xi is equal to the limit M tends to infinity, mu x of b xi 1 over M divided by mu naught of b xi 1 over M, right? This is true for all xi in E sub x, and the measure of mu naught of E sub x is 1. Then I can look at the intersection, E sub x intersect E, right? So this also has measure 1. And for all xi in the intersection, I get that on the one hand, because xi belongs to E, I know that d mu x d mu naught of xi this is equal to the limit of these functions. These functions are exactly my functions f xi m of x, right? So yeah, so this is equal to f xi m of x because I belong to E. So this limit on E is equal to the limit of f xi m of x, which is my definition, by definition, pxi. And so I get that pxi is equal to d mu x by d mu naught of xi for all xi in this full measure set, Ex intersect E. Okay. That's it. So this was just a little bit of work that to show that the Poisson kernel, the domain is actually a product set, right? M cross E, where E has full measure. Otherwise, for each X, you would get a different full measure set, E sub X, and so on. It would not be a product space, right? So anyway, this is just a little bit of work one has to do. Actually, what Anderson and Shun show is much stronger. They show that actually in the xi variable, P of xi is continuous. It's actually continuous in the xi variable. And this is actually, so it extends to a function on all of boundary M uniquely. There's a unique continuous extension. And they show, in fact, it's Holder continuous in xi. So they show much more, but I mean, those proofs, that takes much more work than what we did. So that's why I avoided it, because that would have been too long. That would have been too long. So yeah, that would have been quite too long. So what I did is more or less what we can do by soft methods without going into too many calculations. So I mean, to finish, I suppose maybe I should end this by stating the question that we can think of, right? So we have so P from M cross boundary M. Let me call this P0. Yeah. M cross boundary M to 0 infinity. The Poisson kernel. Such that one for all xi in boundary M, x goes to P of xi is harmonic. And two, we have the Poisson formula in the following sense. So we know the Poisson formula for continuous functions, right? So in fact, we have a Poisson formula for bounded harmonic functions. That's what Anderson and Shun prove also. So for all bounded harmonic functions, okay, let me give a couple of representation formula. Yeah, okay, that will make it clear. So for all bounded harmonic functions U on N, there exists for any, okay, so let me say for any bounded harmonic function, there exists, say, a phi in L infinity M, L infinity boundary M, such that U of x is equal to integral over boundary M phi xi P of xi, P naught of xi, d mu naught of psi. Yeah. So this is for bounded harmonic functions. And then you have actually what Anderson and Schoen show using the Martin boundary is that for any positive harmonic function, U on M, there exists a finite Borel measure say nu on boundary M such that U of X is equal to integral over boundary M P of X psi d nu of psi. Okay, for all X in M. So you have this representation formula for positive harmonic functions as integral of the Poisson kernel with respect to a finite Borel measure. Okay. So this is a generalization of the Herglotz representation formula for positive harmonic functions in the unit disk or the upper half plane, right? And so.
But here this boundary is same. You said something, Martin boundary.
Yes, yes. So actually what they prove is that the Martin boundary is homeomorphic to the visual boundary. That's the main
and
result.
And this P is same as P0.
So, yes, yes. Sorry, it's P0. Yeah, P0.
Okay.
Okay, so why am I writing P0? Okay, let me explain. So why am I writing P0? Because suppose I take suppose the spectrum of the Laplacian is minus infinity to minus lambda 1. Okay.
Right.
Where lambda 1 is lambda 1 of M. This is positive. Okay. If this sectional curvature is less than a negative constant, then one can show this bottom of the spectrum is positive. Okay. Okay. So then what Ancona shows is that the following. For any lambda outside the spectrum, okay. So spectrum is L2 spectrum, okay, L2 spectrum. So this is so the interval from minus lambda 1 up to plus infinity. Okay. We have a function P lambda from M cross boundary M. Again, it's a positive function. Such that one
So you get eigenfunctions.
for all, right? So for all xi in boundary M, the Laplacian of P lambda of dot comma xi is equal to lambda
P lambda.
P lambda dot comma xi. And 2, if U is positive on M and is a lambda eigenfunction, and so delta U is lambda U, then we have the same statement. There exists a finite Borel measure on boundary M, the visual boundary. Okay, this is the same boundary, the visual boundary. Mu on boundary M. Such that U of X is integral over boundary M. P lambda xi d nu of xi for all x. Okay. So for every xi, you get a positive lambda eigenfunction, P of xi, and these give you all positive eigenfunctions. Okay, by integrating over xi with respect to some finite Borel measure on the boundary.
So they have constructed this P lambda, is it?
Yes, yes. So actually, how do you get the P lambda? I can explain that. You can get the P lambda as follows. So you fix an origin, right? Okay. Now for every point x, there is a unique Green's function. So let me call this G sub lambda x. Okay. So with pole at x, so what this function satisfies is that delta minus lambda I of G lambda comma x, this is equal to minus Dirac at x.
Yeah.
Okay. So it's an eigenfunction outside the point x. It's an eigenfunction, right? So if lambda is 0, then this is the usual harmonic Green's function with pole at x. Okay. But this works for any lambda. Lambda is bigger than minus lambda 1. So in fact, this G lambda x, you can give an explicit formula for this. G lambda x of y is equal to integral from 0 to infinity e to the lambda t p of xyt, where p of xyt is the heat kernel. This is the heat kernel. So if lambda is 0, it's just the integral of the heat kernel dt in the t variable. Otherwise, it's e to the lambda t. The point is this integral converges for lambda bigger than minus lambda 1. Okay. This integral converges for lambda bigger than minus lambda 1 because this heat kernel satisfies a decay in the t variable.
Right.
Yeah, so it's less than some functions of x. And then you have there's an e to the minus lambda 1 t factor here. Yeah. Which you don't see in Rn. You only see in negatively curved spaces. This extra exponential, you see when there's negative curvature. So yeah. Okay. So this is this Green's function G lambda x. Okay. So this is positive, right? Because the heat kernel is positive. This is positive. So now what you can do is you define a function k lambda x of y is g lambda x of y divided by g lambda x of 0. So you just normalize it so that the value at the origin is 1. Okay. So this is the normalized Green's function. Okay. Right. So now what you do is, then the fact is, for any xi in boundary M, this is a highly non-trivial fact. Okay. As x tends to xi, the limit x tend to xi of k lambda x y, this exists. And this is equal to your p lambda of x
Okay.
xi.
Complicated construct.
So let me say one thing, at least you can see that this, if I look at this k lambda x, this is a positive eigenfunction, right? This is a positive eigenfunction with just a pole at x, but its value at the origin is 1, right? So as x goes to infinity, if I look at a compact set, on this compact set, it has no poles. It is an positive eigenfunction, and the value at the origin is fixed. So by the Harnack-Yau inequality, this function and its gradient will be uniformly bounded on compacts, right? By the Harnack-Yau inequality. Remember, the Harnack-Yau inequality we proved actually for eigenfunctions also, for positive eigenfunctions, if you look at it. So we can always say that this has a subsequential limit, right? By Arzela-Ascoli, this has a subsequence which will converge to some positive eigenfunction. Okay. But in fact, the limit exists. Okay. The limit exists. And this is no matter which way you converge to the boundary point xi. So yeah, the question is, all of these somehow use positivity. Okay. So, I mean, for me at least, it seems quite a natural question. What happens if lambda is complex? Right. So how far can you go? Well, actually, this integral makes sense here. This g lambda x, this integral will also converge for just the real part of lambda bigger than minus lambda 1, right?
Right, it's just Laplace transform, right?
Yeah,
In t variable.
Yes, that's right. That's right. That's right. That's right. So, I mean, this only depends on the real part, right? The modulus only depends on the real part of lambda. So this will converge also for real part of lambda bigger than minus lambda 1, right? So, I mean, what Anderson and Schoen have done is basically, if here is the lambda plane, then let's see. So the spectrum is up to here. Let's say this is minus lambda 1. Okay. This is the spectrum. Now here you have 0, right? So here you have P0. Okay. And what Ancona has done is, for every lambda on the real line outside the spectrum, you have a P lambda.
Right.
Okay. But now the question is, your G lambda, which you're using to define this P lambda, these G lambdas make sense also in this half plane. Right?
Right.
So can you define a P lambda outside the real axis, right? a complex p lambda? That is the question. And then prove some sort of representation formula. So you won't be able to talk about positive eigenfunctions. There'll be complex eigenfunctions, but what kind of complex eigenfunctions can you represent, if you can represent? So, I mean, there are lots of questions to think about here. The main thing would be to show is this limit exists, right? If you can show this limit exists, I think a lot can be done already. So first of all, can you show that at least this sequence is equicontinuous? So then you would have to prove a Harnack-Yau inequality for complex eigenfunctions. So not positive. So that's the first question. Can you prove a Harnack-Yau inequality for complex eigenfunctions? So these are the things I've been thinking about a bit. So I don't have much. So Arkujit Utsav, if you're interested, we can talk about this next semester. We can think about this.
This Helgason conjecture was not proved in NA group, right?
You should know better than me. I don't know.
I have never seen it.
Yeah. Because I mean, as far as I know, I mean, I've seen only the little bit the proof for real hyperbolic space. Even there, you use the decomposition into K types, right?
Not there.
That's not there. Yeah. Once you have the decomposition into K types, then you get a regular singular ODE, and using that you can analyze. You can analyze the eigenfunctions, right? There's a lot of structure there. Yeah. In NA groups, I don't think you have a description of all eigenfunctions.
Right.
No, I don't think so. Yeah. So anyway, even this Ancona's result doesn't give you all eigenfunctions. It gives you for lambda real and outside the spectrum, it gives you for positive eigenfunctions. Right. So the key point is positivity is very important in this. Yeah. Positivity is very important. So can you go beyond positivity when you go to complex eigenfunctions? Is there some substitute? I don't know. I don't know what to do.
Only thing that comes to mind is giving some size estimate that you find that LP eigenfunctions or something like that.
Yeah, that may be, yeah. But those are a bit different positivity, because I mean LP eigenfunctions will give you an LQ function on boundary.
Right.
But positivity gives you a measure on boundary, not a function. It gives you a measure on boundary.
No, I'm saying when you are going to the complex thing.
Right. Even there, yes.
Yeah, you have to give some kind of restriction, right?
Some restriction, yeah. Just some LQ, LP estimate, yeah. I can't think of anything else really, so yeah. But I mean, what I mean to say is, for harmonic manifolds, this P lambda exists. So in particular for symmetric spaces and Dimitrich spaces, this P lambda, right, for harmonic manifolds.
For symmetric spaces, it is easy.
This actually works.
I mean.
So for harmonic manifolds, let me just say 1 second. So if I've used lambda here. Let me use mu. Okay, so for mu, real part of mu, let's say bigger than minus lambda 1. Choose lambda such that mu is equal to minus lambda squared plus rho squared. Okay. So we're taking some sort of square root of mu here. Then P mu of x xi is e to the I lambda minus rho b xi x. That's so you see, this lambda is what? Lambda is a square root of mu, right? So lambda is
mu plus rho square.
minus mu minus rho
Right.
squared, right? So actually what happens is when you go around in the mu plane, this is really the mu plane that I'm looking at. The eigenvalue plane is the mu plane. You'll have an analytic continuation of the lambda,
Mhm.
you see, because you have a square root, right? So when you go around, this minus lambda 1 is, this is minus rho squared, right? So when you go around this minus rho squared, you'll have an analytic continuation in the lambda parameter. So, yeah. So anyway, these are all things to think about. So I guess maybe that brings the course to an end. But we can talk about this when we meet otherwise. Yeah, we can talk about these things more if you want. So anyway, thank you for attending the course.
Yeah,
I hope
thank
it
you
was
for the
helpful.
course.
So,
Yeah.
okay, thank you. Thank you. Yeah, thank you. Okay, so I'll send you the notes for today and then, yeah, so we can talk about these when we meet. Yeah. Okay, all right. Bye then. Bye. Bye.
14.